Welcome, everyone. So it is my pleasure to introduce today's speaker, Volker Wulfmeyer. And many of you know him much better than I do, because he's had strong ties with EOL for quite a while. And he actually did his PhD work at the Max Planck Institute and at the University of Hamburg. And then he did a postdoc at the University of Hamburg before he moved to Boulder to become a research fellow at NCAR. And he actually then became the leader of the Lidar group here in EOL, or actually it was still ATD at that time. And then he moved back to Germany in 2001 and became a full professor at the University of Hohenheim in Stuttgart. And I believe he's still there. He has won numerous prizes and awards, and he was an NCAR affiliate scientist for 3 years. And one of the awards that caught my eye is the award of the United Arab Emirates Research Program for Rain Enhancement Sciences. I thought that sounds very interesting. But that's not today's topic. Today's topic is planetary boundary layer studies with LiDAR synergy. And with that, I'll pass it on to Volker.
Yeah, thank you very much for the introduction. It's a great pleasure to be back in Boulder to work with many scientists at NCAR and NOAA on studies of the planetary boundary layer with LiDAR synergy. I structured my talk in the following manner. First of all, I would like to motivate this research by addressing a couple of key challenges in Earth system modeling, mainly from the perspective from our university. Then I show you some examples of turbulence studies using a special combination of LiDAR systems. These LiDAR systems are very accurate nowadays. They measure water vapor, temperature, and wind profiles with high resolution, so that these systems are also very useful for data assimilation studies. I would like to show you one example of that. And then we come to a new remote sensing system we developed at our university. We call it ARTOS, the atmospheric Raman temperature and humidity sounder. I would like to end my talk with a vision. Recently, at our university, we developed a land system model which consists of the following components. For the atmospheric part, we use the WRF model, and the land model is NOAA-MP. So this is basically already the setup now of a model system to do forecasts or regional climate studies. However, the dynamics of the vegetation is still frozen, and also a couple of processes in the soil are not considered. So here we added a crop growth model, which we call GCROSS, which provides now dynamic plant variables, like the growth of the canopy, the change of the leaf area index during the simulation period of the model. And furthermore, we added also some processes considering the CN cycle in the soil, which is important when you consider the simulation of plants by agricultural activities. Then we developed a model integration layer and combined this model with the land use decision model, which is basically a multi-agent system. Now, while the model is running, let's assume if you make a climate simulation, the climate conditions are feeding back to the decision of the farmers. Considering that 50% of the surface in Europe is driven by agricultural activities, and also 50% of the land in Germany, it's of course very important to consider these kind of feedbacks. So then the model output, like crop growth and crop yield, also yield quality, is delivered to the farmers, and this model decides basically what crops they will grow in the next year. And this is feeding back and changing land use. And then the model develops, and then we assume that the land atmosphere feedback processes are better represented. Also, this model considers external factors, agropolitical factors, demographic development, economy, and so on. We implemented the G-cross model, and here you can see a run over a couple of months, where you see on the right-hand side the standard frozen setup of WRF, where the leaf area index is provided by a satellite data set of a couple of years earlier. On the right-hand side, you see the coupled model run. Now, the differences are obvious. Now you see the growth of the vegetation. It's mainly winter wheat we implemented in the model system. Can be expected that the differences in the feedback to the atmosphere is, of course, substantial, because the leaf area index show these great differences. And then implemented in the model, there's, of course, a decision process when the farmers start the harvesting. This usually takes place in July. And now you can see the multi-agent systems tells us, okay, the crops are ready to be harvested and the leaf area index is changing. This is an example to point out that these kind of human feedback processes are nowadays really essential to make model forecasts, maybe not in the weather forecast range, but at least on the seasonal scale and also on the climate scale. So do we see any differences in the feedback between the land and the atmosphere when we now implement the G-cross model? This is indeed the case. We used here a two-legged coupling index between soil moisture and daytime latent heat flux, coupled with a maximum of CAPE, which is achieved during daytime. And the strength of this feedback index shows you how strong soil, latent heat, and CAPE is coupled. You can see that in the frozen configuration, the index is not very strong, but it increases considerably in the model run with dynamic vegetation. Consequently, we can state that the effects of dynamic vegetation are very important. And what I do not show here, but this was also a result, is that the model bias with respect to comparison with observations during this time period was reduced by 1 Kelvin. And this is actually of the same order of magnitude like the climate change signal. Yeah, is this true? No, other models are doing a good job. This is, of course, always the question we ask, and we can only address this when we have better observations. When we start to evaluate land atmosphere feedback, this requires that we have very good observations, of course, of the land surface and the vegetation states, but also of the atmospheric boundary layer. So we need very high resolution profiles of temperature, water vapor, and dynamics to validate whether this feedback is correct as simulated in this model system. For this purpose, I would like to show you some results of a combination of LiDAR systems. The results were mainly collected during a field campaign which took place at the Southern Great Plains site of the atmospheric radiation program in Oklahoma, and the field campaign was called the Land Atmosphere Feedback Experiment. This took place in August 2017. The key instruments are a water vapor Raman Lidar, operated as the SGP site, and here we co-deployed this with a vertical steering Doppler Lidar and a 6-beam steering Doppler Lidar. So these were located pretty much at the same position. And then we added 3 other LiDAR systems. One was the NOAA Doppler Lidar Dalek from NOAA CSD. You can see it here. And then 2 LiDARs we brought from our university to this location. This is the rotational Raman Lidar you can see here, which provides now high resolution temperature profiles. And the system has also scanning capability. And here we have our water vapor dial, which provides high resolution water vapor profiles. Yeah, what can we do with these instruments? Assume now we steer with all the instruments vertical. Then you can, of course, get the time height cross-section of temperature. This is a measurement over a couple of hours at the site from the 30th of August, as an example. Well, you can see now that the Raman lidar is capable to monitor very nicely the evolution of the temperature field. The vertical resolution of the data is here, in this case, 50 meters, and the temporal resolution 10 seconds. And this enables us, of course, also to look at the turbulent fluctuations of temperature. You can see now the variability in temperature, where we just subtract the mean of temperature at each height. Please note the scale. This is just plus minus 1 Kelvin. And you can see nicely the warm updrafts below clouds, the dry and colder air entrainment in between. And when you look at these data, you find that the statistical error of these kind of measurements is now just a few tenths of kelvins, so that we can really resolve these processes. At the same time, we operate at the water vapor dial. Of course, you get also a time height cross-section of these results. You can look at the water vapor fluctuations, and this is now given in grams per cubic meters, so that's absolute humidity. Again, you can see the updrafts below the clouds, very nice and sharp entrainment processes. It looks like that most of these entrainment processes actually reach the ground, which may be a problem for the Monin-Obukov similarity theory. Here also a very strong entrainment process. We had actually two water vapor lidar systems at the place, also the SGP Raman lidar. And these are the corresponding fluctuations coming from the Raman lidar. You see actually a quite good agreement, but the water vapor dial has a much better signal-to-noise ratio, obviously. And this is, of course, something we want to achieve when we operate a water vapor dial. It's a high-power system. Okay, it must be worth the effort to run a high-power water vapor dial. And then we also had the vertical wind measurements of the Doppler lidar. You can see also nicely the updrafts of the vertical wind here, positive vertical wind, and the entrainment processes. So the Doppler lidar, of course, also a nice instrument to look at the wind structure. So what can we now do with these systems? First of all, we can evaluate the turbulent fluctuations with respect of the three variables, vertical wind temperature and water vapor, to get variance profiles. That's already a nice output. This is now actually one of the first examples where we are able to run the instruments really routinely over a longer time period, so that we can see even the time height cross-section of the variance. So to my knowledge, this is rather new, that this can be done maybe not for the vertical velocity, but also now for water vapor. So we see now over the time period the evolution of the water vapor variance as well, which reaches a maximum at the interfacial layer at the top of the boundary layer, and we see actually also some trends in the variance in the mixed layer. When we compare that with the Raman lidar, we get actually quite good agreement. Also here the trend is resembled, and when we compare the profiles, the variance profiles over 1 hour during this time period, actually you can see that both instruments can do the job not to resolve water vapor variance profiles. What can we do with these data? Well, we can investigate the water vapor variance budget. This is one thing we now started to evaluate, but this requires also the covariance between W prime, Q prime, for example. So we have to measure also the latent heat flux profile. And there are also some interesting higher order moments which have to be determined. That's one study which is now possible with the combination of these systems. Another way to use the data is actually to find and to investigate relationships between the variance profiles and gradients. This is basically a starting point of a turbulence parameterization. You may take the variance, simulate the variance profiles using these gradient relationships which can be retrieved from the mesoscale models. and used then the parameterized variance for shallow convection parameterization, for example. And we derived a relationship a while ago, basically in a paper in 2016, and we have some new results now in an updated paper where we can see here the variance and then a couple of gradients. So how does it really look like? The original idea to come up with these relationships using scaling variables came from Sorbian in his papers 2005 and 2006. And this relationship then was evaluated in our paper 2016 with respect to Lidar data. So when you now look at this equation, it turns out using specific scaling variables that the water vapor variance is related to a constant, the convective velocity scale, and then the ratio of the water vapor gradient over the Brunt-Weisseler frequency. This index I indicates the interfacial layer, so this just holds for now for the interfacial layer. And then Sorbian suggested, okay, there should be also a relationship between the maximum of the variance and the interfacial layer and the wind shear. And therefore he proposed that there should be a function independence on the Richardson number, which is nothing else, so that's a gradient Richardson number, which is n squared over Si squared, and this is the wind shear on the interfacial layer. Now, what we can measure is, of course, Ri. We have wind profiles, we have the temperature profiles. We can measure the water vapor gradient, we can measure the temperature gradient, we can measure the convective velocity scale. So everything what is here in red can be measured now and put in relation to each other. This allows us actually, first of all, to evaluate what is the function? What is the function of the variance independence on the Richardson number? Sorbian proposed this kind of relationship in his papers, that there should be this kind of functional relationship. Now we took a quite long data set from the SGP side using the Raman Lidar and the wind profiles and temperature profiles and found the following result. Here you can see the ratio of the variance due to the gradient functions, and here the derivation of the Richardson number. And actually we find this is constant. There's no relationship. It's a constant relationship. So in contrast to Sorbian, we found that the variance, at least for these cases we selected, is just dependent on the water vapor gradient and the Brunt-Weisseler frequency, and the functional dependence on the Richardson number is a constant. I would also like to point out that you see on the left-hand side the data we took from the LiDARs. On the right-hand side, Thijs Heus did LES model simulations for the same cases using the micro HH model, and he found basically the same result. Of course, the question is, why is there no dependence on wind shear? We can maybe discuss that later. Well, if the relationship is simpler, it's of course also very nice to develop turbulence parameterizations. Okay, let me move on with some other examples. Of course, when we now point with all systems vertical, we can get W prime, T prime, Q prime, so we can determine the covariances. So this is now basically routinely possible. And here you can see probably the first measurement of the time height section of the sensible heat flux at the site. The sensible heat flux is obviously not constant. It increases in time here. I have to say that we are not 100% sure what's going on here, that the heat flux is going down again. We have to evaluate the data more in detail. It's of course more challenging to look at the covariances between two variables rather than at the variance at one variable. What is promising is that you can see that in the interfacial layer, the sensible heat flux is changing sign. That's really negative as it should be. And then we can, of course, also look at the latent heat flux. Latent heat flux shows an increase of the divergence during the time. And here the issue is that the latent heat flux actually does not reach the maximum at Zi, on the interfacial layer, but rolls off a couple of 100 meters below, which makes it here more complicated to relate the maximum of the latent heat flux also to gradient functions. This is currently, as I said, a work in progress. It's not really 100% clear how far we can go here. Don?
What are the scales here? The vertical resolution and the time scale?
We used data with a resolution of 10 seconds, and the vertical resolution was 50 meters. Yeah.
Okay. Is this like a pencil measurement, or is it an average?
Yeah, we point vertical all the time, but of course the turbulence gets advected. And then we average each data, each profile, to get a flux profile, we average the data over 1 hour.
What size is the beam?
The beam size is 10 centimeters, approximately. Yeah, but again, now we average the data, so we have a time series, all 10 seconds at each height, which we use to calculate the covariance, like with an eddy covariance station. I think the beam size doesn't really play an important role because the eddy size is much larger. So we sample the eddies quite accurately. I will come back to this when I show you the autocovariance function. Yeah, so these are now ways to get a sensible heat flux profile and the latent heat flux profile at the same time. Yeah, but they are really definitely don't look like a textbook example, not that you expect a nice slope of the flux profile and nothing else is going on. We see a couple of meso-microscale variability during this measurement, which obviously make it difficult to get a representative flux. What we're planning to do is to relate the flux, for example, to a gradient relationship, which was also derived in our paper. Or we can investigate the water vapor budget. We get the tendency term with the Lidar, and we get the divergence of the flux. The advection term, the notorious advection term, is of course more complicated, but we are now studying within the LAFE campaign with a triangle of LiDAR systems or passive remote sensing systems, whether we get also a handle on the advection. So this is currently the status of the measurements of fluxes. It's possible, but it's very challenging to evaluate this. There's no question about it. Okay, let me now come to the third example, what we can do with these kind of measurements. And this brings me back to the autocovariance function. So we usually measure the autocovariance function with a time step of 10 seconds. So one lag is 10 seconds, and then you can plot the autocovariance function here. This is now an example for the absolute humidity. Of course, at lag 0, now the total variance is the atmospheric variance plus the noise variance. And now we can, if the resolution of the measurements is high enough, then we resolve the inertial subrange, subsample this so that we can assume that in this region up to the 0 crossing, the autocovariance function behaves as atmospheric variance minus structure function coefficients times tau to 2/3. And when we do the fit, this is the red function, it fits the data quite well. So we get, with this kind of analysis, now the water vapor variance, because we can extrapolate the structure function to lag 0 and get to the noise variance and can separate this from the atmospheric variance. This is, of course, the work or the analysis which has been basically initiated for LiDAR data in Don Lenshaw's paper of 2000 in JTAG. We do this now routinely for these kind of data. But we get actually a bit more. We can look at the 0 crossing here of the autocovariance function and measure the area. And this area actually gives us the integral time scale, which is a kind of measure of the mean size of the eddies in time, why they are advecting over the side. And this can be shown that the area, which is an independent measurement, divided by the variance is nothing else than the integral time scale. It can also be shown that this is 2/5, the zero crossing. And this can be related now to the structure function, also just using this relationship as 2/5, the variance divided by k, 3/2. So we get basically, by measuring the integral scale and the variance, we can get k, the structure function coefficient. Okay, what can we do with that? Yeah, of course, as I mentioned already, we must make sure that the temporal resolution of Lidar measurements is substantially higher than the integral scale, but this is fulfilled for all measurements we do throughout the boundary layer up to the interfacial layer. Usually we use 10 seconds. The vertical wind integral scale is typically of the order of 50 seconds. And water vapor and temperature is usually a bit higher. It's like 100 to 150 seconds. So what can we do? We can get the k coefficients and relate this to the variance. So here's now shown the variance in specific humidity or potential temperature. And when we now evaluate this, we find actually a very accurate linear relationship between the variance here and the k coefficient. And what is also interesting is that the coefficients are pretty much the same for potential temperature and for water vapor. And so this could be a possibility, without measuring the structure function, that we can relate in the future variance measurements to the structure function coefficient. That was one result coming out of this. So they're really remarkably proportional, the k coefficients to the variances, and have the same coefficients, pretty much. But we can even go a step further. We can now actually investigate one term in the water vapor variance budget, which is called the molecular destruction of variance. This is a term which is basically equivalent to the TKE dissipation rate, but now it holds for water vapor variance and temperature variance. Let's call it here n rho over bar. When we now look at the structure function coefficients, when we do this technique for vertical wind and have at the same time horizontal wind profiles, we can actually get a profile of the TKE dissipation rate. That's actually a nice output, using a vertical staring Doppler lidar. Okay, but we can also do the same exercise for k rho and n rho over bar. And after some mathematical combinations, we actually find that n rho over bar is the function of the k coefficients we can measure when we measure vertical wind and water vapor at the same time. And we have also get the horizontal wind profile. We can express this in dependence of the k, of the structure function coefficients, or in terms of the variances and the integral scales. And the same thing can be done for kt. So we can relate the kt coefficient to the molecular destruction of variance. And I did this for a data set from the so-called HOPE campaign in Jülich, and here you get the profile. What is shown here, the molecular destruction rate of specific humidity variance in grams per kilograms per second. It reaches a maximum in the interfacial layer, and we get here values of the order of 5 times 10 to minus 5 grams per kilograms, grams square per kilogram square per second. It would be actually very nice now to make some comparisons with LES or some other observations, whether this order of magnitude is right. But I cannot say too much about this, I have to say. And the same thing we can do with temperature. The temperature data were at this time a bit more noisier. The signal-to-noise ratio and the temperature fluctuations was noisier, but nevertheless, you see also here a maximum of this molecular destruction with a similar order of magnitude, 5 times 10 to minus 5 Kelvin squared per second. So these are the examples I would like to show you today concerning the application of the synergy of these instruments to make turbulent studies. Okay, then I would like also to point out, it's not only that we have now with these instruments a better insight maybe in turbulent transport. When you just take the mean profile of the water vapor dial, with of course also very application of the new NCAR water vapor dial. Or you take the SGP Raman lidar, or maybe other lidars which are around, and you add also temperature. The vertical resolution of these systems and the accuracy is that high that they can basically be right away assimilated. Now, the bias is much lower than when you compare that to other remote sensing systems like passive remote sensing systems, and the vertical resolution is much higher. Now, we can go throughout the boundary layer to the lower troposphere, typically with a vertical resolution of 100 meters. Whereas a microwave radiometer at a height of 2 kilometers has a vertical resolution of 2 kilometers. It's not very meaningful to get a vertical profile. So then the task is now to demonstrate the impact of these LiDAR systems. And here we evaluate two types of data assimilation techniques. One is a standard 3D VAR, three-dimensional variation technique. And the second one is that we combine now our 3D VAR with a hybrid ETKF. And you can see how it works. Now we produce 10 ensemble members which are perturbed. Then we run these for a while to start at a certain time the data assimilation process. We calculate the ensemble mean of these members and get 10 perturbations. These perturbations are plugged in the ETKF gain matrix. Here basically the perturbations are corrected with respect to observations. And then we get the corrected perturbations. At the same time, the ensemble mean is used to get an updated analysis of the mean using a 3D VAR ETKF. This is basically a 3D VAR, cost function minimization, but the new thing when you combine these techniques is that also the error covariance matrix of the model gets updated by the ETKF. So that means that the error covariance matrix of the model becomes flow dependent, which is of course a big advantage when you combine this here. So we get an updated mean, we have our 10 corrected perturbations, we add this to the mean, and then you continue with the 10-member forecast. The hybrid approach has also the advantage that by the stabilization of the ensemble by the 3D VAR, you don't need so many ensemble members. Typically, it can be shown that you really would like to have 80 to 100 ensemble members to run just an ETKF. Here, we can just run 10 ensemble members by this hybrid approach and still have a consistent rapid update cycle. So this is quite convenient, and when we now here started, we usually take ECMWF analysis, we run the model from a certain time, first of all when everything gets started for 18 hours to minimize the spin up between our model system and the ECMWF initial values. Then we update the data assimilation process each hour. First of all, use just conventional data like weather stations, soundings or so. Here, it's green, because this forces the model already to the conventional data. And then we continue and add either just the Raman LiDAR temperature profiles, this is here in blue, or both, so the water vapor dial plus temperature Raman LiDAR. So finally, in the final configuration, we assimilate water vapor and temperature profiles simultaneously. Here you can see the setup of the instruments. We took data from the HOPE campaign, which took place April-May 2013 in Jülich, which is the middle west of Germany. You can see the WRF configuration, but I think I have to move on, otherwise I'm running out of time. Let me show you the results. This is now shown here on the left-hand side. So these are the water vapor profiles, and here we have the temperature profiles. What is shown here in light orange is the water vapor dial profile we used for the assimilation, and in pink we have the radiosonde. We did not assimilate the radiosonde, we just used the radiosonde for verification. So they were quite close, but the dial data are averaged over 50 minutes. And of course, you can expect a perfect agreement between a snapshot from a radiosonde and a 50-minute mean coming from the dial. Now we started the data assimilation process. Yeah, on the right-hand side, actually, we have here the temperature profile of the Raman lidar and from the radiosonde. Okay, what you show here, first of all, is the profile of the model system without any data assimilation. It's a solid black line. Of course, you see substantial deviations. The non-conventional, the no data assimilation does not reproduce the depth of the boundary layer, and it's here off in terms of temperature. When we now add the 3D VAR, conventional data assimilation, we don't see really a good improvement in the water vapor, but we see a substantial improvement in the temperature because it's a very mixed boundary layer. If you have a surface weather station close by, of course the dry adiabatic temperature gradient is then produced in the model system. But there are still some deviations here at the top of the boundary layer. So the dashed results, I forgot to mention this, are the results we just achieved with a 3D VAR. On the solid line is then 3D VAR EDKF hybrid. And do the hybrid, you see actually already quite a nice improvement of the water vapor profile, not so much in temperature. And here we just used the conventional data in green. Now we added the Raman lidar temperature data, the 3D VAR. It gets a bit closer to the water vapor and also here a bit closer to the temperature profile. When we do the hybrid EDKF, it's very similar. So when we just assimilate the temperature data, the 3D VAR and the hybrid approach seem to perform similar. But when we now add also the water vapor plus temperature and take the conventional profile, and it gets closer here, but we see still substantial deviations in the boundary layer. Here it gets better also in the free troposphere. And last but not least, when we add the red line, which is the hybrid approach, water vapor dial plus temperature, we get actually a very nice agreement. That this water vapor profile is corrected also here in the boundary layer, quite close to the observation. And here we get a good agreement with the temperature profile above the boundary layer and also here inside the boundary layer. The reason for that actually is that that the error covariance between the water vapor and the temperature is frozen in the 3D VAR, but it becomes dynamic and corrected in the hybrid approach. And this is obviously what we can see here. The model gets more flexible to get adapted to the correct temperature and water vapor profiles. So it seems so that it's really important to assimilate, to use a hybrid approach when you want to assimilate water vapor and temperature profiles simultaneously. Yes?
About the boundary layer, the dial seems to be biased with respect to the sun.
Yeah, you may also say that the radiosonde is biased with respect to the dial. The radiosonde is a snapshot, it's just one launch, and we average for a while. It's very difficult to say. You may think that the radiosonde does not really have substantial errors when we calibrate it correctly. But here we compare a snapshot with a 50-minute of the dial profile. So we saw also some trends in the water vapor field. This may explain the deviations. And also the sounding is drifting somewhere. Then you have a distance between the vertical profile of the lidar and the sounding. I just illustrate this to show you what the radiosonde delivered. I think in the future we have to get a bit more sophisticated with respect to these comparisons. Maybe use another lidar for verification. Yeah. Excuse me?
The observation.
The observation error, yeah, this is actually not really visible on the screen. On my computer looks better. We have actually here shading around the profile. Sorry. Yeah, the projector doesn't show it. No, this is actually quite clear, quite straightforward with the LiDARs. When we average the data over 50 minutes, for example, which is actually a quite good averaging time for a grid box, we get basically the atmospheric variance and the noise variance. We can separate this, as I showed you, with the autocovariance function. So we get basically a noise error profile in height. We get this with each LiDAR profile. For each step we assimilate again, we get again an error profile. This holds for water vapor LiDAR and for the temperature. However, we don't use only the error profiles coming from the noise. We combine this in order to get also a handle on the representativeness error. Now we basically take the total variance over the 50 minutes. But the total variance, as I showed you, is a noise variance plus atmospheric variance. And when you have a curtain of LiDAR data over 50 minutes, the atmospheric variance may give you the idea how variable the water vapor field is and how representative the water vapor profile is for the grid box. That's currently the best thing I can think about and to get also a good idea about the representativeness, independent of any other observations. So, for instance, if the noise error is getting high, sorry that you cannot see it, but it's of course larger high. The error is mainly determined by the noise. When we go closer, it's mainly determined by the atmospheric variance, but it never reaches unrealistic values, which is not very nice for a data assimilation system. Does that answer your question? Okay. So finally, I would like to show you some slides concerning a new system which is quite useful to make these kind of measurements really routine. Now we have, of course, the problem that we design wonderful field campaigns, putting all these sophisticated instruments together. Then we have our measurements over a couple of weeks. We evaluate this. We can, of course, make nice research and get some ideas and new insights in turbulence. But of course, when we want to understand this, we need a very good statistical database. So the goal should be to have actually, exactly these measurements routinely, 24/7 at a certain site. And this is actually the goal of this development. We developed here Raman temperature humidity sounder, which we call ATOS, which is incorporated in a box. Here you can see two air conditioners. It consists of a rather strong laser transmitter which operates in the UV, a receiving unit, data acquisition system, here's a UPS, and here the receiving telescope. Here you can see a control computer and the diode laser controller for the laser and cooling device. So this system got significantly smaller than any other Raman LiDAR we have for now. Now the width is 2.6 meters. It can be managed. The weight is about 900 kilos. Actually, we can now put this LiDAR system in an airplane and transport it to another site, which was previously really quite difficult. A quite large operation range, and the power consuming is approximately 3 kilowatts. So this is operational. It runs all the time. It can rain, it can snow, doesn't matter. The snow is melting, the raindrops are evaporating, and then we continue our measurements. The water vapor profiles are basically provided in real time with error estimates. Here you can see an example of a measurement we did recently at our new Land Atmosphere Feedback Observatory, LAFO, which we currently set up at our university. Shown is here the time-height cross-section of the water vapor mixing ratio. The temporal resolution is 10 seconds and the vertical resolution 100 meters throughout the troposphere. And you can really see now fine structures now can be resolved. We see here the evolution of the convective boundary layer, here dry layer on top of it. This is a rain event, so partly this can actually be penetrated with a LiDAR. Here are clouds and rain, but also here there's some range we can even achieve to measure in clouds. At the same time, we get the temperature. The temperature is actually even better behaved because the signals are stronger. In this Raman Lidar techniques, the rotational Raman signals are proportional to the oxygen and nitrogen number density, whereas the water vapor signal is proportional to the Raman scattering of water vapor, which is variable. And basically what you can see here is that this system measures pretty much in all climate zones with the same performance, and due to this homogeneous Raman backscatter. If you would like to know more about this system, I also would like to introduce Andreas Behrendt, the master of this system, who did a fantastic job developing this system with Diego Lange at our university. Again, temperature, time, height, cross-section, 10 seconds, 100 meters. You see basically not really a big difference between day and nighttime anymore. And this is, of course, now attenuated by clouds and rain. But otherwise, you can really see fine structures, see the inversion layer evolving at the top of the convective bound layer. We have a vertical resolution that we can measure the inversion on top of it, how this is evolving. So this is now really a very nice progress. And first of all, really was surprised when I looked at the raw data that we don't need to, sometimes we don't need to average. This is now the raw data resolution we usually use, 10 seconds in time and 7.5 meters in the vertical. And you can see here day and nighttime measurement. This is actually a fog event in the morning. You can see the very strong gradient of moisture on top of the humid layer, some convection developing. And this is at the same time temperature, 7.5 meters in the vertical. You see the inversion layers. We have a couple of cases where we can see now the inversion layers in the free troposphere, which is so important for data assimilation. This makes a difference whether convection is initiated or not, whether you have a certain lid sitting there in the middle troposphere. Now we can resolve this daytime and nighttime. So this is a quite good progress, but I think I have to come to the end soon. Let me just show you a movie, what is the typical output of this. The raw data output, 7.5 meters, 10 seconds. This is temperature, this is mixing ratio, and this is the backscatter ratio. Convective bound layer development. When we see the afternoon, another convective bound layer development, rain event, afternoon decay, nighttime measurement. Very fine structures, wave-like activities. We see Kelvin-Helmholtz stabilities on top of these layers. If you're interested, I can show you later on some more results. And of course, when we now have these kind of resolutions, we can get temperature variance and water vapor variance profiles with a very high accuracy. Now here, this is a case where we had actually a quite stable bound layer, but gravity wave activity on top of this. And then we can measure the water vapor variance and the temperature variance. And the scale, the maximum of the temperature variance here on top is just 0.2 Kelvin squared. And here we can even measure the variance down to 0.01, 0.02 Kelvin squared, which corresponds to a couple of tenths Kelvins. So this is now the state of the art, I would say, what we can do with the Raman Lidar. So what is now the next step? And this is actually my vision, finally, I would like to present today. When we have now these systems available, wind measurement, temperature, and water vapor, we should put these together and have these systems at the same time operational. And I proposed this recently at a meeting of the Global Land Atmosphere System Study, which is a big project of the Global Energy and Water Exchange Experiment. And I call it now the GLAS, Land Atmosphere Feedback Observatories, or GLAFOs. The idea is to measure continuously in the soil, get profiles in the soil, temperature and moisture, to get profiles in the canopy. Also profiles in the canopy are important, moisture and temperature. And the surface layer profiles, which here are a couple of new instruments available, the Raman scattering fibers, for example, which have actually a vertical resolution of a few centimeters. And then we add the lidars. And this is really a true observatory to measure land atmosphere feedback, because then finally we see the gradients in each layer, which are strongly related to each other. So this could look like the following. This is actually based now on the larvae experiment. We have the heterogeneous land surface, equip this with the soil sensors and detailed sensors in the canopy. Then we add the LiDAR systems. We have a combination which is running vertical, providing all the variances and covariances. We get the horizontal wind profile with scanning LiDAR systems. And last but not least, when we add also scanning LiDARs, then we can move it back and forth in order to get profiles of water vapor, temperature, and wind down to the canopy top. And then we can really see the full interaction between the different layers. Yeah, we proposed this to the glass panel, and I hope that this will be the next step to continue with the turbulence research and also the data assimilation efforts I showed to you today. Thank you very much.
There are questions, and I would ask you to please use the microphone so it gets into the webcast.
Are all these studies on flat terrain?
No, flat terrain, yes, but still heterogeneous with respect to the land use, the land cover.
But regarding complex terrain, what do you think you will do in an area with complex terrain?
I think in complex terrain we need to combine vertical steering LiDARs with scanning LiDARs in order to investigate also the flow structures and the transport processes in complex terrain. The LiDAR systems we developed in Hohenheim have also scanning capabilities. We applied this also during larvae. Here the goal was to measure profiles of temperature and moisture very close to the canopy over different land use. But in principle, you can do that also in orographic terrain and study the two-dimensional variability. This is very challenging, of course, to investigate this, that just one vertical turbulence profile is not really representative. But if you combine this with the transport processes from scanning systems, I think it will also advance our understanding with respect to the interaction of turbulent processes and mesoscale transport.
One comment I make. If you verify forecasts from your data simulation system rather than the analysis, you don't need another independent LiDAR. And that's, after all, the important mission of data simulation, to see if you can. So you can use your same LiDAR to verify your forecasts.
That's a possibility. We need more of these, which you usually do not have. But actually, we started with some data assimilation efforts with Meteo Swiss together. And they studied the impact of their Raman LiDAR in relation to precipitation events, which could be one solution here. To assimilate the LiDAR data in the pre-convective environment and study the impact of the LiDAR data assimilation with respect to convection initiation. And if the model does a better job to get the timing and the spatial distribution of clouds and precipitation better by the impact study, then I think it's also a proof that LiDAR systems have a positive influence on the forecast. And then the verification is not done with LiDAR data, it's done just with the precipitation field. Mm-hmm. This is definitely our goal. We just don't want only to assimilate the data to get the water vapor fields and the temperature fields better. Of course, one of the visions here is that we think that the LiDARs fill a gap in the observations of water vapor and temperature, leading to a better prediction of extreme events, including extreme precipitation.
So what are the trade-offs between the Raman water vapor measurement and the dial water vapor measurement?
The trade-off, there are a couple of trade-offs with respect to water vapor. The Raman lidar finally is limited at a certain amount of mixing ratio during daytime to get a good signal-to-noise ratio. So if the mixing ratio is going down, drier and drier and drier, then you lose signal-to-noise ratio. Whereas the water vapor dial does not have this issue because you can tune then to a strong water vapor absorption line, and you get basically the same relative error in the water vapor profile. We did not see really a big problem with our measurements yet with the Raman lidar. There was always enough moisture available not to get really these kind of nice results. This is one point. And the other point is that a dial in Raman lidar behaves different with respect to the dependence of the noise error on range resolution. Now, if you plot the error profiles at the same range resolution, usually the dial gets better with coarser range resolution, but it could be still good enough to resolve turbulence. And then there's a certain crossing point, and when you increase the range resolution, the Raman lidar can become at a certain point better because the signal-to-noise ratio is proportional to the square of the increase in range resolution. Whereas the dial is delta R changed in range resolution to 1.5. So you can win more in signal-to-noise ratio when you make the vertical resolution coarser. Yeah. It depends, of course, on the design point, on the average power of the lidars, where this crossing point is. And basically, I can say with the new Raman lidar, we moved this crossing point far during daytime, that we have good data measurements. Well, when this system is actually indeed commercially available, it's a spin-off of our university now. Compared to a Doppler lidar, it's basically the double price like a Doppler lidar. Compared to a radiometer, it's also the double, but the information content is orders of magnitudes higher because we had water vapor and temperature. So basically, I think it should have has the same price like a cloud radar. But considering the huge information content you get with prognostic variables, I think it's really worthwhile now that we now start to set up networks of with these systems to get continuous data with respect to temperature and water vapor.
Volker, is there a layman's explanation, not being an instrument guy, why your measurements start at 300 meters? Mm-hmm. And is there a possibility of applying a trick such that, let's say, you only measure from 10 meters to a kilometer?
Mm-hmm. Yeah, we're thinking about this trick for a long time. Good idea. Mm-hmm. The issue is the following. We have a pretty large telescope. We narrow the field of view down to reduce the daylight background. And when you're then in the center of the telescope sending out the beam, then you have this kind of overlap function, which starts with our system, I think, at about 200, 300 meters. So with one system, one telescope, it's difficult. But you can add another one. You can actually add another small telescope for the near range, where the signals are very strong, with a larger field of view. So this, from my point of view, would be the best solution that we can go down. I cannot say exactly for now how far we can go down, maybe 50 meters or so. This should be possible when we combine both telescopes. And finally, of course, and this was also the goal of our development, is that we apply a scanner. When we scan down low, we can actually go down to the canopy top. And we did it already. Now we made temperature and water vapor measurements with actually a height resolution of 2-3 meters from the canopy top to the mixed layer.
That's what I want.
Okay.
No, especially for nighttime stuff and things like that.
Yeah.
The excitement happens closer to the ground.
I fully agree with you. This is traditionally we focus on daytime because there's also most of the music playing with respect to convection initiation and cloud development and these kind of things. But I fully agree with you that we should think more in the future how to apply these systems also in the nocturnal bound layer, and particularly, I think also what will be very interesting to study the transition periods, the afternoon decay and the buildup of the bound layer, and also the daytime evolution of the convective bound layer. We have actually, I did not showed it actually last year in my talk here. We have a very nice movie where we did continuous scans with a water vapor dial. We saw the evolution of the transition from the convective bound layer to the stable nocturnal bound layer. So we have data actually on this already. We're very happy to provide this from the LAFE campaign. Over several IOPs we have these low-level scans now. And we have wind profiles, temperature profiles, and moisture profiles simultaneously.
There are more questions? Then let's thank our speaker again.